refreshed and bright-eyed and bushy-tailed and ready to put you in a headlock again and just shove the information into your brain until it's coming out your ears. So, it's going to be a fun day. All right. So, quick review of the PE type stuff that we went over yesterday. All right, so we talked a couple of times about the Windows loader and what it's doing with respect to when you double-click on executables. It's taking your executable, mapping it into memory at some location, and then going out and finding all your prerequisite libraries and mapping them into locations in memory, finding any prerequisite libraries they have and mapping them into memory. And then after it does all that, it goes back through and it calls the initial entry point, the address of entry point in the PE header on each of them, if they have it set. And then eventually it makes its way back to your WickedSuiteApp.exe, calls the address of entry point on that, and then starts executing the code for your program. So, let's see. Then, of course, we've been digging into this PE format all day yesterday, most of the day. And again, I highly recommend reading these two. I couldn't even learn PE stuff just in one reading of these. It took, many readings of these. So if you go back and you read those two articles, I think you'll get some more information that will reinforce what you see here. All right, and then the first thing we went over was the DOS header, and we said DOS header is simple. There's only two things we care about. There's the eMagic field, which is just MZ, and then there's the eLFA new field, which just points us to the next header, which is the NT header. All right, so then we get to the NT header, and that's basically just has a signature field, which is that null EP, so that in little endian order it's PE null. And then we had the file header and the optional header, and those structures are each embedded within this header, right? Embedded within this. That's why you see, that's why it jumps from 4 to hex 18. That's saying that's the size of this file header right there. And then from hex 18 to wherever, that's the size of the optional header. So then we dug into the file header. And here, there was only a couple things we cared about. We cared about the time date stamp, which was a timestamp which is set at link time, which says when this file was linked. And we said that we can use it sort of like a unique identifier for different versions of executables as they're compiled. Each time they're compiled, they're going to get that updated. We saw eventually how during the OS checking bound imports and things like that, it actually checks time date stamps to make sure that, versions that were bound against, if your imports were bound against a specific version of a module, that's what it uses as the version, basically. We said number of sections is one we care about as well because it's covered up right now, but there were those section headers that were immediately after the optional header. And then the characteristics was the sort of the lamest of the characteristics that we've seen. It's just things like I'm a DLL, I'm executable, I'm 32-bit or 64-bit compatible. Right, and then we talked about those section headers. I think that's what's coming up next. We said that number of sections is just telling you how many of this array of section headers there are immediately after the NT header. And then there was also that optional header within the NT header. And there were a couple of things. That address of entry point, that's a big one because if you have some malware or something and you don't know anything else about it and you want to set a breakpoint on the first code that's executing, in the absence of the thread local storage, which we'll talk about today, that address of entry point is going to be the first place that the OS starts executing code within that module. Image base is just where it prefers to load into memory. We said executables on non-ALSR systems like XP, they're always going to get their image base. DLLs will get it if it's free. Otherwise, they'll get moved around and put somewhere else. And kernel modules, it doesn't care at all. It'll just load it wherever. Section alignment and file alignment, those were just for when we're mapping from file into memory. Section alignment was saying, I want my sections to start on boundaries of hex 1000 or whatever. File alignment is just saying when I'm writing my sections onto disk, they should be in chunks of hex 200 or hex 80 or whatever. And Drew pointed out yesterday that the hex 80 turns out to be the sector size on floppy disks, actually. So that's interesting. That's where that came from. So some of the modules you'll see have hex 80 as their file alignment. Size of image, that was the total virtual size that the OS loader needs to allocate in order to map this file into memory. DLL characteristics, that had those variety of security characteristics like ALSR compatibility, NX compatibility, whether or not you're going to do a signature check on the binary, digital signature check, and things like no SEH, as well as some other ones that you can read about later. And then data directory was the big one. This has all those pointers to other data structures within the file, such as the imports, exports, debug information, etc. Then, yeah, so here's the data directory. And the section headers, right, so the section headers, we care about most of the stuff here. The name, that's where the .text, .data, .reloc, whatever, that's stored in the name, and the name is just an 8-byte array, and again, it's not guaranteed to be null terminated, so if you're going around trying to like copy the names out of sections and stuff like that, don't use string copy. It's gonna, if it's an 8-character name of a section, you're gonna cause a buffer overflow or something. Then we had that one union, but we said we only ever care about virtual size, so misc.virtualSize is always going to be the total size of the section in memory. So it's telling the OS loader, you must allocate this much virtual memory for me. The size of raw data, that's the total size on disk. So you're mapping size of raw data, number of bytes, into memory at virtual size. And so we said, one of them could be bigger, one of them could be smaller. So if size of raw data is small and virtual size is big, that's typically sort of implying something about like a BSS allocation. You're just allocating some memory for variables which didn't have an initialized value and therefore didn't need to be on disk. If size of raw data is big and virtual size is small, that's implying that your section happened to be padded basically due to that file alignment. So we can say, well, my section only has 4 bytes, but due to file alignment, I had to write hex 200 bytes. Therefore, the size of raw data could be small, or could be big, and the virtual size could be small. And then the virtual address is just the start of the virtual size. So you start at virtual address and you go for virtual size. Pointer to raw data is the offset into the file where you find the data. So pointer to raw data is you start at this location in the file, and then you go for size of raw data. So each of them is just basically saying, this range of file, this range of virtual memory, OS loader, do the right thing, map this into that. And then the characteristics, those were things like read, write, execute, pageable, stuff like that. Those were the kind of characteristics that we deal with for section headers right here. Right, so you can say your memory is writable, it's readable, it's executable, it's shared, which means shared between processes potentially. Not paged, it's saying like OS loader never take this and like map it back out to disk. Discardable is saying like it may be used immediately when the OS loader is doing whatever it needs to do, but then it'll throw it away. It's telling the OS loader, look, this data that you mapped in, you can throw it away once you're done with it. And other things like just initialized data, uninitialized data, and code. And then we spent a lot of time going over imports, right? So we know that this data directory entry, index 1, right here in the data directory, is the image directory entry import. And all it is just a virtual size, a virtual address and a size. The virtual address is an RVA. It's saying, here's the relative virtual address within the file where my information about imports starts. And size is just saying, here's the total size of a bunch of these import descriptors. So it's knowing that this is going to be an array of these image import descriptors, right? You got 1, 2, 3, 4 here. So we've got an array of these. Typically, the last one's going to be null terminated. It's just going to be an entry, a descriptor that has all 0 in all of its fields. And we said for the image import descriptor, there's a couple things. We said for this normal case, our normal, quote, normal imports, we said this is always 0, this time date stamp. And we actually saw that the forwarder chain turned out to be 0 most of the time as well. But on the other hand, if we have bound imports, this is -1. So time date stamp will be -1 if it's bound. Forwarder chain will be, -1 if no forwarders. That's what we saw for the bound imports. So really don't care about the forwarder chain much for now. So the main things, those are just the two fields we don't really care about. The main one is the original first thunk, which that pointed at our import names table, and the first thunk, which pointed at the import address table. And so there's one of these descriptors for each module. That's why it has a name field. It says, here's my imports from ntdll.dll. Here's my imports from user32.dll. Here's my imports from kernel32.dll, and they're all just going to be an array, one after another, at the location that data directory pointed to. So again, name just says this module's information refers to user32.dll or whatever, and then it's got some pointer into some offset in the import names table or import address table. And so what this part of the picture is actually trying to show then is, this is trying to show that little thing that I showed as, one column here, and something in the middle. This stuff right here, that's the stuff in the middle. So I kind of just blew through this, but this stuff right here is the stuff in the middle. And what it's trying to say is those two columns, the import names table or import address table, each of them is really an image thunk data kind of structure, but this was just a union that had 4 possible interpretations. And we said that initially always the import names table is considered to be this p image import by name. So it's always assumed to be a pointer to one of these structures. And we said that for the import address table, it also starts like this. It starts with pointing to one of these data structures so that they're both pointing to the middle. But eventually it gets rewritten to be PD word and interpreted like a function. And that's just saying that eventually the import address table gets filled in with real addresses. So again, this was an image thunk data array right here. So each of these, they're really just a D word, but they have those 4 possible interpretations for that union. All right, so that's image thunk data array. That's an image thunk data array. This one, because it's pointed to by original first thunk, is what we call the import names table. This one, because it's pointed to by first thunk, is what we call the import address table. And on disk, they both just point to the exact same thing, this image import by name. Right? And that structure is basically just a hint, which is an ordinal and then a string. And again, that hint, that ordinal is, we haven't learned about ordinals yet because we haven't done exports, but you can basically just think of it like there's going to be some big array of functions that my module exports. So if I'm a DLL and I export modules, I'm going to have a big array of functions and say export 0 is this function, export 1 is this function. And that hint field is basically telling the OS loader, go to the exports of this module and try that index first in its exports. So it's saying if you want to find IO delete symbolic link, try, index 14b in the exports of ntos kernel.exe first. If it can't find it at that specific index, then it just goes back through and searches over, searches for the string IO delete symbolic link through the entirety of the exports, but turns out it can do a binary search, but we'll get there. And so, we spent a lot of time on imports, and then we saw one variant of imports. Oh, sorry. And then, right, so this was the key thing that we were talking about yesterday, right? On disk, import address table, import names table, they both just point at those int string kind of structures. Eventually, in memory, we went through Notepad, or Telnet, Notepad, I don't remember which. It was Telnet. We went through Telnet, and we saw that in memory, Telnet had all of its import address table filled in with real function pointers. So, then we saw one variant of that yesterday. We said that, in memory, that import address table gets filled in. The variant was just saying that on disk, we can go ahead and fill that import address table in with things. And that was the bound imports. Right. So bound imports, in order for a thing to have bound imports, it does have to have a non-zero value in this data directory entry. Oh, actually, I skipped one thing. Just as it was just a miscellaneous thing, but as a miscellaneous thing, there is a data directory entry which specifically is pointing at the base of the import address table. So if you want to go directly to the import address table and see what's there, you can always just go to this entry, this image directory entry IAT, which will be index whatever it is, looks like about 13 to me. So it's some index in the data directory, and that'll give you the RVA of the very start of the import address table. And of course, we did that IAT hooking thing yesterday where we injected the DLL we injected this AppInit hook IAT DLL into the task manager, and it basically just changed the import address table entry for anti-query system information to redirect to the attacker's version, and the attacker's version always just removes calc.exe from it. And so that's the basis of user space rootkits. All right, so then again, bound imports. In order for something to have bound imports, in order for the OS to at least recognize that something has bound imports, this bound import entry in the data directory needs to be filled in. And this entry is going to be pointing at some array of descriptors for bound imports. And that array of descriptors looked basically like this. It was just each of those descriptors had a time date stamp, a name, and then forwarders, which we don't care about forwarders. We'll come back to that when we learn about forwarded exports. So the point was just that bound entry points at the start of this. So here it would have been RVA 250. I have the column in VA mode, but it would have been RVA 250. And so for each of these, they're basically just there to help out the OS to do a sanity check. The point of bound imports is it was just a speed hack to make it so that the OS loader doesn't have to go around and fill in all of those import address table entries with, the real function pointers. At link time, the linker just fills in all of those actual function pointers. And then at load time, the loader just needs to say, do I think any of those would have changed? And the only way they would have changed is if the version of shell 32 that I, the OS loader, am going to load up, if that's not still this time date stamp that, and if the version of comctl 32 is not still the time date stamp that. So the OS loader just needs to go down the line and say, okay, well, I can see that this, notepad requires comdlg32.dll. I can see it needs this for its imports. I just need to now check, is the version that I'm going to load up from disk and put into memory, is that the same version as there? If so, I don't have to do anything. If not, then I'll just have to do my normal imports procedure of searching the exports and filling in the import address table. So that data directory pointed at this. And then the big difference with an executable like Notepad, which has bound imports, is that when you go in, you look at the import address table, you'll see that they have, a bunch of real-looking function pointers in there, right? So probably, comctl has 773.0.0.0 as its base. Advanced API probably has 77D.0.0.0 as its base, and then some offset into those modules is this real function pointer. Yes?
Well, if it doesn't find the correct version, it's the versions, what does it do?
It does the exact same thing it would normally do. So in this case, the import names table is still the way that it would always be. So if we look at something like Notepad, right? So if we look at the import address table, we see that it's all filled in, right? If the OS comes along and it says, okay, well, the advanced API, it goes to the bound directory, right? And it's searching down, and it gets here and it says, oh, it looks like the advanced API 32.dll that I'm going to load that's actually on disk right now is not the same time date stamp as this. If so, then just go ahead and head back to the names table. And the names table is still the same way that it always looks. It's a pointer at these structures, which are a hint and then a string. And so it just goes through and it says, okay, well, I'm going to do whatever I would have normally done in order to look up reg query value XW, reg close key, reg create key, etc.
So something that's already loaded in.
Right. It'll just, load whatever's already, it'll load whatever version it has. And then if it's not the same version as the bound imports expects, it'll just resolve the function pointers the same way it always would have. Pretending, it's like, think that, if you didn't have bound imports, the OS loader's job was to go around and find the real function pointer addresses for each of these strings, right? So for each of these functions which have a string saying, I need that function and that function and that function, the OS loader's job is to go out to the exports of each of those functions and find the real offset into that function, which is, specifies reg query value XW. So the OS loader, the point is just when bound imports fails in the sense that if the module is not the same version, it just falls back to doing the same thing it would always do for non-bound imports and just resolve them the same way. Going back to this names table. All right, and I think, yes, go ahead, Chris.
Yeah, was there anything that we've seen so far that would have prevented you from doing what you had done the other day with the DLL and the putting in the malicious DLL?
Is there anything we've seen so far that would have prevented the injection of the DLL? Is that the question?
Like the timestamp. Yes. Yes. Are there any of those fields with the dynamic binding, checking, anything that would have prevented that?
So the point is, well, the thing that should have prevented this ostensibly is the fact that the section where, so let's look at this notepad for instance, right? In Notepad, the import address table we can see is in the section.txt, right? So some chunk of the .txt section is the import address table. Now if we look at the permissions for the .txt section, it says, okay, this is code, this is executable, and this is readable. So ostensibly this should not be writable, right? So that is what ideally is trying to stop attackers, but in reality this is not trying to stop malice, this is trying to stop accidents, right? So it's trying to stop someone from accidentally overwriting something in the .txt section. And I, as the attacker there, all I did was I called a function, virtual protect, which just says, for virtual protect, it's like, let's see, if you're familiar with Linux, it's mprotect, I think, on Linux. It's just a function which says, you give it a virtual address, and you give it the permissions you want, and you give it a size. So you say, starting at this virtual address, for this size, I want this to now be read, write, execute, something like that. And so in that thing, I just, the attacker can just overwrite the permissions of the section and set it to writable. So no, there's nothing inherent in the executable structures or anything like that which is trying to stop an attacker from doing that sort of thing. It's really additional controls which are necessary in terms of, how do you stop them from getting into the memory space in the first place? Because once they're in the memory space, they have the same permissions as the code which they're running within. So
you'd have to put in a major monitor with lots of legs and extensions to do things like that.
Bill, could you turn him up just a little bit? And say again, Chris, you said something like a Linux monitor or something?
You'd have to put in a major monitor of some kind that would, or some kind of major control plane that would disallow that, being it's been designed for a different purpose.
Right, exactly.
Actually, without major changes to the operating system.
Right, exactly. And the point is, attackers are typically leveraging some inherent capability in the OS. So there was that registry key that just let them load any DLL into memory. There's APIs by which, you can read and write to other processes' memory space. We said that, ostensibly, Notepad's process space should be completely separate from Calc's address space. But Windows has APIs such that as long as they're, have sufficient privileges, they can open a handle to the other process and write memory into there, start a thread in there, etc. So if you go to that Wikipedia page on DLL injection, it'll show the variety of ways, each of which is pretty much utilizing legitimate system functionality in order to get into the memory space. And you can always set different access control things on that. You can say, you know, there was one commercial security product I looked at that they say they have the permissions set correctly so that if you try to open up their process in order to write into their memory, then it's prevented, basically. And so Windows does have the capability for access control on some of these features as well. It's just a question of whether it's being used. So we just talked about the bound imports, right? And just the only other thing to say is that you know, when we go back to the normal import directory, so this was the normal import directory, the only difference here is, you know, this still points at the imports names table, this still points at the import address table, but those two, time date stamp and forward chain were -1. So. And then we just made a point yesterday about why I think binding is being deprecated, because as address-based layout randomization is being used more, it's address-based layout randomization says, you know, I want to move around my modules in memory. Binding says, I'm assuming that these addresses will be fixed and they'll always get whatever's in the header. So when ALSR is being used, most of the time the binding is not going to be correct anyways. There's no, you know, there's no harm in doing the binding still, right? You can still do the binding and maybe you'll get lucky and maybe this module will be located at the base address that the linker assumed at link time. But, I mean, it'll just be a small overhead on your point and on your part and a little bit of space overhead. But since it's not going to work most of the time, they're sort of at odds with each other. So that brings us to our new topic for today, which is going to be the last thing about importing. And this is delay-loaded DLLs. So thus far what we've seen is that a module specifies via that import directory which modules it needs to import. So it's, if I'm Notepad, I require shell32.dll and user32.dll and whatever else. That's all specified in that import directory, that big array of structures, each of which has a name that says I'm this module and that module. Those work under the assumption that at runtime, when you double-click on an executable or whatever, the OS loader goes around and it goes through that entire list and it pulls them all into memory right now, and it resolves all the function pointers right now, and it sticks them into your import table, and then it runs. So the point is, that's a lot of upfront work, essentially, for modules which you may or may not actually use. So, you know, if I, in that case of, say, let's say that Task Manager, right, it used NT query system information to show that list of processes, right? But until you actually click on the tab that shows that list of processes, right, it probably has never called that function. And so if that was the only function that it calls in ntdll.dll, then theoretically you didn't even need it ever until you clicked into that tab and it requested the list of loaded modules, loaded executables. So delay-loaded DLLs are basically trying to delay the performance impact of, you know, loading everything up all at the very beginning. So by default, Windows goes with a strategy of let's just load it all up right up front, and then, you know, we'll run after that. And so actually Linux goes the opposite direction. It says I'm only going to load stuff when necessary. So this delay load DLLs is very similar to what, if we get to the Linux section, what you'll see on Linux. So, right. So all I'm saying with the second bullet is just there's going to be another data directory entry that has to do with delay loaded DLLs. All right. So one thing is just, so the point, okay, well, I should say more clearly. Right. So the whole point of delay loaded DLLs is you're telling the linker, which in turn sets the right structure for the PE format. You're saying, I don't want you to load this module until I call the function within it. So it's basically saying, just load it just in time, right before I'm about to call a function. Otherwise, you know, don't even bother loading this into my space. Don't even bother resolving import addresses, stuff like that. So how you specify that at least is in Visual Studio in the linker thing. There's an import thing that says delay loaded DLLs. And so you just list DLLs. You'd say, this DLL I don't want loaded until I eventually call a function from it. And then there's just an option about whether you want to allow to unload that DLL. So you could theoretically load up a DLL, call a function, and then say, okay, well, I'm calling it once and never again, and then unload it. And the reason why you might do that is to save memory, for instance, right? So, if I have my library, and I know that, no one else uses my library, but I don't want to be taking up extra physical memory, I can say, if I load my thing up into memory, I'll run whatever functions, but then maybe I'll throw it back out of memory and only ever load it again if necessary. So, sort of a time-space trade-off, essentially. So it'll take me more time to run my code to be bringing the DLL in and kicking the DLL out, but simultaneously I'll be using less physical memory. So, all right. Yeah, this is where I got lazy with my zoom effect. See? So blink, 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 bam. No more zoom effects. All right. So down here, whatever index this is, image, directory, entry, delay, import, looks like index 14 to me. It's 14, 15. There's 16 data directory things defined, or 16 data directory entries in the data directory, but only 15 of them have an actual index defined. So that's why I'm saying this is 14, because that's 15, because there is no 16. Although I guess it'd be index 13. Anyways, oh, well, I'm not that lazy apparently. That one's still zoomed. So, again, so what we're seeing, the emerging pattern here for all this import stuff is we point at some array of descriptors. Except, actually, I said that too soon because I think there's only one of these. We'll see. All right, so there's two main things that we care about in this image delay descriptor. The first one is RVA IAT. So the RVA IAT, let's see, move that over. What this is there's actually a separate import address table for all these delay loaded modules. Okay? So you've got your normal import address table, and then for anything that you bring into memory just in time, it gets its own import address table. And so one of the questions I got in the other class was, why? Why does it have a separate import address table? Why can't you just fill in the real import address table just in time? And that has to do, again, with those permissions on the original import address table. The real import address table is marked as non-writable after the OS, writes a bunch of stuff, then it marks it as non-writable. So the point with delayed imports is at some point, at some random point in the execution, the OS loader is going to come along and fill in these entries. And so if they were marked as non-writable, then the OS would have to mark them as writable, write, mark them as non-writable again. And so instead it just creates this separate import address table in a writable section like .data, and then it just goes ahead and fills it in just in time. And yeah, the RVA DLL name, that's just saying that this is the DLL which is going to import. So yes, actually there is going to be an array of these descriptors. And then we're not going to care about the other ones for now. Right. So how, roughly speaking, how this is going to work, and I show it with a nice picture next, but I'll just say it first and then show it and then say it again. Roughly speaking, how this is going to work. The initial, delay load import address table, it has addresses in it, but each of those addresses calls to some little stub code, which eventually calls to code which loads the module if necessary, resolves the address if necessary, and sticks the address back in the import address table. So this is basically the same way that Linux does it. And what was I going to say? I don't remember. Right. So, oh yeah. So I mean, the thing I wanted to say was that, before when we were looking at those calls to imported functions, right, we know that they had call some address in a table, and we had the understanding that, with this square bracket form of the call, it's going to go out to that memory address, pull in the import address, pull in the function pointer that should be loaded in that import address table, and call to that function at that function pointer. So in this case, again, we're going to see it calling to an address that's in some table. And here what I'm saying is this is my delayed loaded import address table. And so this address right here, 103E636C4, right? That's the table address. So it's calling the table address, and it's taking whatever value is in that table right now, and it's calling to that. So initially, so here's the point of the delay load table. Initially, this address, which is in the table, is actually pointing at some stub code somewhere within the module itself. So it's like it's trying to call draw theme background, which I think in this example is in like uxtheme.dll. So it's trying to call some imported function draw theme background. But initially, when it just executes the code as is, the initial code is pointing at, the initial entry in the table is pointing at some little subcode here. So the first call goes called, the address there, pulls out that address, and it calls to that address. So now it does this, and then this, and, you know, it jumps somewhere. So if we look at, you know, what that code is actually doing, we can see that actually the stub code that it called to is taking the address of the table where its own address was stored. So it's saying, like, you know, if I call that and it goes here and that goes to right here, the first instruction that it actually does is it just takes and it says, well, I know that my address, you know, 425, I know that my address was stored in a table at 64. And so what it does is it just takes the address of that table entry and it sticks it into EAX. Because eventually, some code somewhere is going to go back and fill in that value, which will now be at EAX. It'll say, you know, we want to overwrite that with the real address of draw theme. And therefore, we need to have where we're going to overwrite it stuck into register. So it takes the address that it's going to overwrite later, sticks it into EAX, and then just jumps to, you know, some common function. So this right here, this ending in 40A, every little chunk of 2 instruction stub code, they all jump to the same function. So they do one instruction, which takes the address of their table entry and puts it in EAX. And the second function is just jump to this common function. And that's what I'm putting right here. This is going to be just generically some code, which is actually, you know, embedded into this executable. And this code is going to go out and it's going to say, okay, well, it looks like you're trying to import something from uxtheme.dll. So I need to go see if that's already loaded. If not, load it up. And then I need to go and resolve the actual address of draw theme background. What is that? Okay. I think this is differently animated than it was on my computer, but yeah. So the point is, okay, after 2, we're in there at the DLL loading function resolve code. The first thing that code does is it's going to say if uxtheme.dll is not currently loaded, it's going to load it up. So now that uxtheme is in the memory space of this process. The second thing it's going to do is it's going to go try to find that draw theme background that we're actually looking for. And so that has the address 5AD72BEF. It's going to go find that actual address, and it's going to load that into the same table entry where that was stored before. And again, you know, just if anyone was not watching my awesome animation, all eyes up here, it loads the address into the table. Thank you. All right. So the point is, we were in this code right here, and now that code has loaded the module into memory, and it has resolved the address of the function. So it can go ahead and it can jump to that original function that you were trying to call. So this original function was just trying to call a draw theme background, but it had to go this circuitous route in order to do it. So it went from there down to here, up to there, and then eventually that calls the real function that you were trying to call. And when that's done, it's going to return to right here after the call to draw theme background, because that will still be on the stack. The address of the next instruction will still be on the stack. And when it returns from uxtheme, it will return to the correct place, because, you know, this code right here and that code right there, they all made sure not to, like, screw up the stack or anything. Yes?
Do they have to worry about standard call versus fast call in these cases too?
Do they have to worry about standard call versus fast call? No, I would say no, because basically the issue with standard call versus fast call, right? So when the module is doing something like draw theme, it knows at that time whether this is a standard call or fast call kind of function, right? So at the time that this call instruction is put in, right, surrounding that, there's going to be the pushes above it, and then at the time of compilation, it knows whether or not this is standard call or fast call, actually probably at the time of linking, but therefore, there's either going to be, that add 8 to ESP afterwards or not, right? And so I would say not really. You don't really have to worry about that because the code still knew what it was trying to import. It's just, it's doing the importing in a slightly different way. So the code is still going to be generated the same way. You had a question or not?
I was just going to, I think that code all just gets loaded in by the linker when you click the right box.
This UX theme type code? Or?
All of this method there. And
No, so yeah, I should be clear on that. All of the initial thing that we had on this screen, all this stuff right here, this is all built into, I'm trying to remember where I actually pulled this example from. Maybe it's on my slides next, but this is like based on a real example that I'd pulled in. MS Paint, it looks like. Yep. So all of this code right here, this is the .text section of MS Paint. This is like, this may be in the .text. It may, I believe it's still in the .text section. So like all of this right here is still somewhere in MS Paint. So the issue, so conceptually the notion here is when MS Paint said, I want to use delay loading, the linker said, okay, if you want to use delay loading, I'm going to stick in this blob of code which will delay load your modules. I'm going to stick in all these stub code. So yep, all of that's just in MS Paint. So this is all there whether you click on the things or not. It's just when you do something to, force this delayed loading of something, that's when a call happens to here. That's when this table gets filled in. That's when it loads modules and stuff like that. And we'll see that actually. We'll run through this example with the WinDebug and we'll see it filling these things in on the fly only when we go over and click on something. So anyways, yep, we're in the function resolution code. We move the real function pointer there. We call up to the original draw theme background. It's going to return to after the first call. And now the point here is the first one returned after the first call and ... We eventually got to another one of these calls that looks the same way. But the second time we ever call this, it's going to go directly there because this import address table, the delayed import address table got filled in with the address of the actual function. So initially it has the address of stub code, and eventually it has the address of the real function. And so every time after the first time, it goes directly there. So any further questions on delay loading before we step through and see an example?
Where would the stub code be stored? Oh, is that just in the text section?
I believe it's in the .text section. We'll check here in a second, actually. We'll see it here. I believe it's .text, though. All right. So just in terms of what this stuff actually looks like in PE view, there's going to be, again, PE view is helping us out and saying, okay, it goes and it looks at the delayed import chunk of the data directory, and then it says, okay, at this offset 3A5D8, there's this array of descriptors. And so each of these descriptors has a DLL that it's associated with, and it's saying, okay, well, I'm going to delay load GDI plus DLL and UX theme DLL. And there's the address of the import, there's the RVA of the import names table, which is completely separate from the normal import names table, or import address table, rather. And there's an RVA of the import names table, which actually now I'm curious whether that's in the normal import names table. I have a feeling it is. Check. INT. And then although this thing right here, this RVA to bound IIT is filled in with something, it's non-zero, in reality it's pointing at a 0. So there's nothing there. This is a functionality that's not actually implemented, so pay no attention to the bound IAT behind the curtain. There's nothing there. They didn't ever implement that. So here is an example. Yeah, I'm pretty sure that's .text section. This is an example of what the delayed import looks like on disk, right? So we're looking at PView on disk. And the point is, each of these addresses right here is pointing at some stub code. And I can kind of get a sense of that because the image base for MS point is 1000000, and the size is 57000. So somewhere between 10000 and 1057000, or 1570000, right? These are well within the range of this module itself. So these are addresses in the own module address space. So initially they point to the stub code within itself, and eventually they point to the real functions. And just to spoil things for you, what we see when we actually, what we'll see in WinBug is, you know, there were, say, 3 initial things that were imported from uxtheme.dll, and initially they had those addresses like 103 something, right? And there's a bunch of those addresses still there, but for anything which has actually been called, those will get filled in with real addresses of real functions in uxtheme or wherever else. So we can see, like, here we got a bunch of 103s, and then eventually we have like a 4 EC, and that's like, that one got filled in, so that one's been called, but none of the rest of them have been called, except for those first 2. So let's do that in MS Paint. All right. Open PView first, just to pull up MS Paint. So it is in, again, it's in C:\Windows System 32, MS Paint.
Are we allowed to cheat now and just go to the address labels?
Yeah. All right, so just, you know, I'll show you quick, but yes, you're allowed to just cheat and go directly to it. All right, the whole point here is just that down here in the data directory, there's a non-zero entry for the delay import descriptors entry, right? So that means somewhere within this module, there's going to be delayed import descriptors. And we can find that. So it says RVA 3A5D8. And right there, RVA 3A5D8. And that's if you just click on delay import descriptors in the side there. And so this is saying, you know, these are the modules which I want to delay import, GDI plus and uxtheme. And as usual, there's a null terminating descriptor. And so, yeah, the one thing I want to check right now. So we know that if we go to this RVA import address table, this is separate from the rest of them. So 3E6D4 looks like it's called, let's see, delay names table. 3, what is it? 3E. Is it in the .data section? There we go. All right, yeah, obviously. I said, because it's writable. So .data section, read, write, right? And so delay import table is writable later on. So there's 3 that it's importing from uxtheme. This is what we just saw. Now I want to actually, so it looks like the delayed names table is separate from, interesting. Oh no, see, this PView is trying to be overly helpful, right? So there's actually nothing within this table right now which would tell me that it's, you know, draw theme background and stuff like that. It's just like adding the import names table information to the import address table right now. So in the actual, in the delay import names table, which looks like it is completely separate from the normal import names table, it does have your typical RVA pointing to, you know, a hint, which in this case is all zeros for all of these, and then a string. So if we went to 3A868 right now, we should see 00 draw theme background. So it looks like it has its own little table of strings and stuff. So if we go to 3A6 something, was it 698? Yeah. So 00 and then the string GDI plus shutdown. All right. So the point here is we see the import address table as it is right now. We're going to open MS Paint in WinDebug, and we're going to watch as it like actually fills in these things. And if you want later, you can, you know, step through and read the code and stuff. But for now, we'll just at a high level see that it is filling in these tables. So Open up WinDebug again. In Programs, Debugging Tools, WinDebug. Then we're going to open executable. And MS Paint is again in C:\Windows System 32. All right, and like before, we're going to drag this into the main window. We can see that it broke after it has some modules loaded, but none of these are going to be, UX theme or anything like that. So, going to expand this, drop that in there, going to get a memory window open, and then we're going to drag that up to the top and split the screen. And actually right away, let me think if I need anything else again. You need a disassembly window. So, hover over, hit Alt-7 or hover over the little 1.0 and pull up a disassembly window. We're going to drop that into split the bottom screen. All right, so this is all we're going to need. So just get memory window on top, command on the bottom, disassembly on the bottom as well. All right, so go back over to PEview, and we said that those addresses in the delay load import names table are addresses of stub code within this module itself, right? So if you go into PEview and you look at the RVA for something, come on, how many PEviews open? So we said that these addresses 103, blah, blah, blah. We're saying that these are actually the addresses of stubs within here. Hold on. All right, so back in PEview, we said that these addresses are stub code within there. So if you grab one of those addresses and put it into the disassembly window, you should see some stub code, like I said. So 103, and actually these are these RVAs or are these actual addresses? I think these are absolute virtual addresses. So 10, 35, 42, 5. I already forgot it. 10, 35, 42, 5. And 35, 42, 5. There we go. So I can actually see two little stub codes right here. I can see here's one move with a jump. Here's one move with a jump. And if I scroll around, I'll probably find some other ones. But all right. So that's one of the stub entries. And let's go ahead and put the import address table into the memory window. So it says it's at RVA 3E6C4. And if we go back and look in WinDebug, it'll tell us where we loaded MS Paint. It says MS Paint got loaded at 100000. We're going to put that plus 3E6C4. And this should be our delayed import address table. Right? And we can see that it looks like it hasn't been filled in with anything yet. Oh, and sorry, and change the display format to long hex like it's up there so that you see a D word at a time. So that was 3E6C4. All right, so that's our delayed import address table. So actually what we're going to do now is we're going to set a breakpoint on, let's just say, this first one, and we'll see when it eventually gets hit. So I'm going to copy the address from the first one. I'm going to do BP for breakpoint and just paste that address in there. And you should see this turn to pinkish red, whatever it is. It doesn't show up on the screen like that, but. And so the point is now, whenever this delay loaded import actually gets called, it's going to call to address 1035425. And at that point, we're going to stop the debugger and we're going to see it and we can start stepping through and watch it eventually import the things. So now I'm going to go ahead and let this run. I'm going to hit is it G? Yes, G. Hit G to let it go, or just hit the little, if there's go F5 up there. So I hit G to let it go, and right now MS Paint is running, but I haven't hit my breakpoint. So the debugger is not at a command window. So MS Paint is running. I can kind of see behind the scenes here that little color palette came up at the bottom. But it hasn't called, you know, GDI plus whatever it is. What this is saying right now, it is not called draw theme background at this point, because if it would have hit my breakpoint. So it's happily running along without ever having called this draw theme background. But I know that it has imported the module at this point. So I'm going to click over to MS Paint, and at this point I expect it to actually hit the breakpoint. So I click over to MS Paint, I brought it up, but now back in WinDebug, I can see that it hit my breakpoint because it did try to call draw theme background. And there's an interesting little thing that I see happened here. This value right here, that hasn't changed. So no one's like called, so this is the first time we've called it. We haven't taken that little function pointer and filled it into this table. But someone has called this second function because we see that got filled in. So we didn't set a breakpoint on it, but actually what it's saying is that it has called open theme data at this point, and that's why that function pointer is filled in. It just hasn't, it's just, this is the first time that it's called draw theme background. So that one's filled in. This one is not yet filled in, but if we start stepping through this code, eventually we'll see this function pointer get updated with the real function pointer address. So we can step through by using the little arrows up here, step into or step over. We're going to step into for now. So if I step into once and then I step into again, I got to the jump. And I said right now, this thing starting with, or ending with 40A, this is the common code which like all of the stub code calls in order to like resolve DLLs and in order to import DLLs and resolve function pointer addresses. And so now at this point, if I just sort of like keep stepping over, eventually what I should see is that this, this function pointer gets filled in. So option F10 or this middle arrow here, if I do step over. Yeah, I'm just going to step over this first call right here, and there we go. So somewhere in that code, so somewhere at ending in 4D6 is the code which actually, you know, resolves the function pointer. And so I can step into that thing. So again, I recommend you do this on your own time. Go back, set a breakpoint on the delay import for MS Paint, and then come back and step through the call. And eventually what you'll see is, well, I'll tell you what you see in a second when I talk about the functions which are going to be in there. So this is just basically showing that, you know, I could set a breakpoint on any of these, and I could like play around, and eventually when I do the right thing, when I modify the behavior of MS Paint such that it calls, you know, draw theme or open theme data, etc., it will then call to the stub code. The stub code will call to the common code. The common code will pull in the DLL if necessary, and then resolve the function pointer. And so that's the long and the short of it with delay loaded imports.